So we're pretty short on time. This is going to be quick. I'm trying to get through the slides pretty quickly so we can get to the demo at the end that Hope's going to show off. But we talked about automating pricing for indexers with 𝗨𝗀𝗂𝗪. We also want indexers to be able to optimally allocate in an automatic way. So we've created this tool between Hope, myself, Howard, and Ford, and it's integrated with the action queue. So end to end, you should be able to get automated price multipliers and automated allocation optimally. So I just want to lay out the optimization problem so that you understand what we mean when we say optimization or what we mean when we say optimal. And the motivation here is to provide indexers with the tool that allows them to allocate optimally with respect to indexing rewards. So we're not considering query fees. We're assuming indexing rewards is a good enough proxy for query fees, and their own preferences. And just understand that the more you put your own preferences in, the less optimal, sort of in a global sense, you're going to be, right? You're changing what is the definition of optimal. Next slide. So the indexing reward, I assume many of you are familiar with this, but I'll go over it pretty quickly. So some indexer I, this notation just means in the set of indexers, if you're not familiar with math notation. So some indexer spends some gas to allocate some stake omega ij, which is just a matrix. Out of its total stake, sigma I stake to the subgraph J. And if you look at, we've tried to standardize our notation across a lot of the work, a lot of the efforts that we do at the graph. So if you look at other documents for other projects, they'll try to stick to the same notation. So subgraph J has psi j token signaled on it, and indexer I receives some indexing reward R sub I based on its allocations and the issuance, the token issuance. So this is the formula that you're probably familiar with, although depending on where you've seen it, it might look slightly different. Although, like I said, now the notation has been standardized, so it should shift to this. So next slide. So intuitively, we sort of think about this indexing reward in two parts. One is the subgraph reward, which we call x sub j. And the subgraph reward is just related to the proportion of signal on a single subgraph versus the signal across all subgraphs. So nothing surprising there. The next slide. And then the indexing reward just takes the subgraph reward and multiplies it by the proportion of how much you have allocated to a subgraph versus how much all other indexers have allocated to that subgraph. You sum that over all subgraphs, you get the indexing reward. So basically, you're trying to allocate to subgraphs with few other indexers or like minimum stake from other indexers with maximum signal. There's sort of this problem going on. So what do you as an indexer control? Well, you just control your allocations, but there are other variables at play here in the network that you really can't control. So we can't optimize over that on your behalf. We can just optimize over what you can control. So despite the fact that we have these three variables in the function, all you can control is this omega I, which are your allocations. And omega I is also constrained in that we don't allow you to short. You can't have a negative allocation. And you can't allocate more stake than you have available to yourself, right? Unless there's some sort of lending or borrowing in the future, this is a non-starter. So next slide. So this is actually what the math ends up looking like, right? So we minimize the negative indexing reward, and the reason we do that is because the indexing reward is a concave function. Flip it upside down, it becomes a convex function. Convex optimization is this big field in mathematics, subject to the constraints that we talked about on the last slide. Next slide. And just briefly, why do we care about the fact that this is convex? So this is convex shape, non-convex shape, non-convex shape. In a convex set, everything, if I pick 2 points inside this shape, the line that connects them is entirely contained within the shape. The nice thing about this, if you look at this non-convex shape, if we're trying to optimize over this, like say I'm trying to move to the right as far as possible in this function, if I move to the right and I hit this boundary, I don't know if I can still move to the right if there's something on the other side. Whereas in convex optimization, I know when I hit the boundary, I'm done. So next slide. And you can generalize the sets to functions, right? So this is a convex function, same principles apply. The line that is here needs to be entirely contained within the range of the function. And in fact, it needs to be greater than or equal to the range. So wonderful thing about convex optimization is that if you have a convex optimization problem, it's solvable in polynomial time, whereas if it's non-convex, it's NP hard, which means that there's no guarantee of a polynomial time algorithm that can solve it. You're just sort of guessing. We do have a more formal write-up if anyone's interested in the mathematics and trying to understand the tool at a more fundamental level. The link's there, you can follow it. at your own discretion. And yeah, all you.
Okay, so I will be showing the demo of allocation opt. So very briefly, we want to first install the tool. We are using Julia for our optimization. And so the first thing is install Julia. And then for macOS, you would want to add your path to local bin. But if you're running it on Linux, it should work pretty much straight out of the box. So to install, we first go into Julia repo and then pretty much follow these steps. You want to install the package and then install a CLI, because we also have a CLI that you can sort of use pretty quickly, easily. And then there's any of the public API that is all shown here, which I think I can go pretty quickly to show you what it looks like. For the documentation here, you can see that there is installation steps and then public API and then parameters. And there is also the usage that goes into the CLI script. What we want to show here today is the action queue. So in cooperation with what Forge was showing earlier, we can do a pretty quick demo on that one. So I think I need to stop sharing this one. And then we can jump into the terminal here. Cool. So ideally, you have also a PFS node, graph node, indexer service, indexer agent running, and then you can also try to get the action queue to work. But so here we have the allocation opt. What we want to do is call the script, and the first parameter is the your own indexer ID, and then we have a file that you can configure that includes whitelist, blacklist, frozen list, and ping list. So this is where the indexer can put their preferences of what subgraphs they want to allocate to. So for example, whitelist is a bunch of allocations that or subgraphs that you consider are good. And then there is blacklist that you just never want to touch. There is ping list that would not change your current allocations. And then there is frozen. Frozen list is the one that we don't want to touch, and then pin list is the one that we really want to allocate to. So we, whether it's very optimal to do so or not, we still want to allocate to the pin list subgraphs. So the third, we also want to consider the GRT we want to spend on each subgraph, and we also want to consider a minimal allocation amount. Which say that it might be optimal to allocate only 0.1 GRT to a subgraph, but you might not want to do so out of your own preference as an indexer. And then we also have the endpoint here for talking to the indexer service, so we can send actions to the action queue, and we also have a endpoint to query the network subgraph. So for this one, we're using the indexer service network, but you can also supply a hosted service mainnet subgraph, or you can use the gateway API. So these are all sort of up to you. So, but it takes a little bit before, in combination with action queue, you should be able to see that after this go through, we would receive it on the indexer agent end. Oh, okay, so here we have what I was talking about, the actual thing that we want to see in the action, in the indexer agent. You can see all these actions. I ran this maybe like 2 minutes ago, so all of these are existing already. I guess it hasn't changed very much, but we can also grab the table here. And we can see that this is supposedly the optimal result that we got from our problem, and we can go through and approve them. I also approved this one just now, so we can go on to the indexer agent one. This is the agent. This is the indexer I'm running on the testnet, and about a few minutes ago, I opened this one through the action queue, which so this is how the stack should flow with the action queue and optimizer integrated. Yeah, you can take questions.
I've got a question. So from the point of view of the indexer, the end user, how many parameters can he or she set or need to set? How
You don't need to say anything.
Yeah.
If you want to set stuff, it's up to you.
at least two, I think, the minimum state.
You don't. I mean, if you want to set that to 0, you can set it to 0. So no, you don't really have to set anything. And of course, the more that you set, the less globally optimum you're going to be.
Right,
But at the same time, we wanted to expose these things because we don't know considerations, or we don't want to pollute sort of the optimization problem with considerations like, okay, this subgraph might be dead, so let's not allocate to this subgraph. So you can blacklist that subgraph. So we're sort of exposing all of those indexer preferences through those blacklist, whitelist stuff.
So ideally, if you leave it all blank, it should just grab the network data and do the true optimal of the network at that very moment. But because we know that indexer know that some subgraphs are harder to index, some subgraphs are easier to fail, we want to allow you to say that I'm just not going to touch this subgraph for now. So this is how we incorporate those.
I guess to put it in different words, like the preferences allow you to add additional constraints to the optimization.
Mm-hmm.
I guess like the major reason that I could see that you would want to set a minimum allocation size is to kind of like, it's like a proxy for considering the marginal cost of allocating versus the marginal benefit of doing so in revenue terms.
Yes.
Is that the kind of intended toggle for managing that, or does the optimizer take that kind of trade-off into consideration with increasing gas costs versus the marginal benefit of doing so?
So right now, our optimization problem solely focus on the indexing rewards. It doesn't include gas costs. So this is one of the reasons we think having a minimum allocation amount makes sense for now. And then if we want to incorporate gas costs, we have other ideas on maybe we want to pay attention to the number of allocations we're opening more. But when we think about this problem with respect to what action queue is doing with gas costs, there's also a difference in maybe we really care about when we think about the revenues at the end after indexing reward and operational costs and gas costs, maybe there is much more that a different direction is thinking about the number of allocations.
So I would think of it as a stopping condition, basically, is the min allocation amount, because the way the optimizer, like next step is working, the trajectory.
Yeah.
You're adding like a subgraph at a time, and then you're adding the most optimal subgraph, the most optimal next subgraph at a time, right? And once you hit a subgraph where you're like allocating less than your min allocation amount, at that point we just say stop.
Yeah, that makes total sense. Because I guess given that allocating to a subgraph reduces the reward per GRT allocated, what kind of would then make sense is that you could eke out infinitely more return by allocating more broadly.
Yeah.
But yeah, it makes total sense because you kind of, as you allocate more and more and more broadly, at some point you reach that minimum bound, and that's the stopping condition.
Exactly.
Yeah, it makes total sense.
Yeah, and that's the same way we will be considering gas costs, for example. We consider it a profit function. Once the profit function reaches some threshold where profit has decreased by adding the next subgraph, at that point we stop. We say, okay, go back and return the last allocation. Because adding gas, adding min allocation, these make the problem non-convex, which means we lose the polynomial time algorithm, which means that we don't have any longer the nice, like quick-ish solution that you see, right? It can run for hours and not find a solution.
Yes.
or months even and not find a solution. So
I guess another thing we can show is actually creating the rules here.
Yeah.
Once.
go ahead.
Yeah, a follow-up if I may.
Yeah.
So when you ran the optimizer, there was an existing allocation in place. Will the optimizer, is one of the actions available to the optimizer to deallocate from an existing allocation?
Yeah.
Okay.
Yeah, and in fact, if you, for example,
There's a reallocation.
There is a
Yeah.
reallocate. So
Okay,
I
in the
guess
table.
here, this is one of the another variation aside from action queue, straight up just printing out the rules here. So you can see that there is one that is stopping the existing allocation, and then there is a warning that says check before submitting, and then this is going to reallocate to the same subgraph.
yeah, and also this code is on GitHub, like Hope showed. It's not in alpha, it's not in beta, it just works. I mean, we're using it, so feel free to use it.
Definitely.
And open to suggestions as well.
Yeah, absolutely. Feel free to submit feature requests or something.
Question. Seems like index allocation optimizer is purely based on the signals and every subscription. Is this correct?
Yes.
Currently, I would say probably within the next week or so, we should have a more robust solution. But we have it like sort of implemented. We want to test it and make sure before we actually release it.
What additional considerations are being added?
Basically, those stopping conditions that we're talking about. So min allocation, allocation lifetime, which will be just considered in terms of profit, gas, which is again in terms of profit, and max number of allocations as well is another thing that you can specify. Like I don't want more than 10 things. I don't want to allocate to more than 10 things.
Do you imagine that this tool might optimize for query fee outcomes at some point? And do you think that that might impact convexity?
So right now we're using Signal as a proxy for query fee volume or query volume, right? Which is hopefully it is actually the case in the future.
Is it a proxy though? Like you're just optimizing for allocation reward outcomes?
Yes, but
they're not
curators
really
are
being
supposed,
considered.
curators get rewarded out of query fees, right? So they're going to get rewarded out of subgraphs with higher query volumes, which means that they're going to signal more on
So-
subgraphs with higher query volume.
Theoretically, the query fee should be on similar proportion of indexing rewards.
Theoretically, but we've
Yes.
seen that that's not the case.
Yes. So, I mean, what you're asking is a good question. Whether it becomes non-convex once we add in query fees, I think the problem is we don't know how we can get that sort of query fee information. optimize
Query fee settled on chain. It's obviously retrospective.
Yeah.
Or maybe the billing subgraph on Polygon.
What?
Maybe the billing subgraph on Polygon.
There's less of a lag.
Okay.
So the one thing I will say about that is that historical data is not necessarily the best here because we don't, it's not a guarantee of what's going to happen at the next time step, which is why we want curation, right? So that we have people that are thinking ahead instead of thinking about the past. So it's something to consider, definitely. I'm not entirely sure how we would go about getting that information in a forward-looking sense, I guess is a better way to put it. Like we would have to make some sort of prediction about the future.
Yeah, which is exactly what curation is supposed to be.
Yeah, at which point, what's the point of curation?
So when's the predictive auto curator?
We'll keep you posted.
I like that.
Gonna predict the signals.